So this is going to be a little bit of a refresher on sequences and series and sort of what they mean. I would really encourage you to go through this yourself and see if you can remember what is a sequence, what does it mean for a sequence to converge, look at some of these sequences and see if you can figure out whether they converge or diverge. And if you can't, that's okay, but it'd be great to think through some of these things and then check your answers. So what is a sequence? Well, technically a sequence is a function whose domain is the set of positive integers. Or a subset of these integers. Whoops. Sometimes it includes 0. Okay, but that's really what a sequence is. It's just a function, but instead of plugging anything in, you are plugging only in 1, 2, 3, 4, 5, 6, 7, etc. What does it mean for a sequence to converge? It means that the limit as n approaches infinity of a sub n equals some number L. So when we are talking about the convergence of sequences, we are really looking at what happens to the sequence as n approaches infinity. What happens as we count that input up towards infinity? Remember, we're talking about integers. So we're talking about 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 30, 40, 50, etc., 100, 200, 1 million, etc. We're looking at integers here. So we are looking at, well, what happens to a sub n as n gets large. And to converge, it must approach some number L. The analog to this for a function would be end behavior. You know, the limit as x approaches infinity of f of x equals L. This, in order to converge, you need to approach a horizontal asymptote. So that's sort of the analog of like, oh, if the end behavior of this function is you head off towards the right, approaches some number L, that looks like a horizontal asymptote. What does it mean for a sequence to be bounded? So bounded just means that, you know, for instance, you've got maybe an upper bound here, a lower bound here, and the sequence stays within those bounds. Monotonic means that it is either always increasing or always decreasing. So this is monotonic. This is monotonic. And this is monotonic. So monotonic just basically means always increasing or always decreasing. So this question number 5 is asking, do we think they converge or diverge? If they converge, what to? If they diverge, to what do they tend? So what we could do is plug in some numbers and see what happens. Of course, a sub 1 here would be 1/2, a sub 2 would be 1/4, a sub 3 would be 1/8. I think these numbers are getting really small. I think this converges to 0. That is my guess, that it converges to 0 because as I multiply 1/2 by itself a bunch of times, I'm just getting smaller and smaller numbers. This one, well, b sub 1 would be 1 minus 1, which is 0. B sub 2 would be 1 plus 1, which would be 2. B sub 3 would be 0. B sub 4 would be 2. While I think that this is bounded, I do not think that this converges to some distinct number. So I'm going to say diverge. 2 to the n. Oh, holy heck. That would be, 2, 4, 8, 16. That diverges to infinity. you know, that's just going to get very big very fast. It's like an exponential function in a certain sense. I mean, I guess this is too, but it's exponential decay. Well, these are not exponential functions. What they really are is geometric sequences, but that is the analog to an exponential function. What about sine n to the n? Well, d sub 1 is going to be sine of 1 to the first power. I don't really know what that is exactly. D sub 2 is going to be sine of 2 to the squared. You know, D sub 3 is going to be sine of 3 cubed. I don't think that this is going to converge. I'm going to say diverge. I think it does some weird things. I think sine n is just bouncing around. This one, well, as n gets large, you know, n approaches infinity, this limit, you've got 1 minus basically 0, right? Because e to the negative infinity is going to 0, all over 1 plus 0, I think. I think this is heading towards 1. So I think this is going to converge to 1 because I think e to the negative n and e to the negative n are basically just going to disappear. This one right here looks like some tricky business. Kind of looks like a difference quotient, doesn't it? You know, and like as n approaches infinity, this is going to 0, this is going to 0. So it kind of looks like you're getting cosine of 2 minus cosine of 2. This kind of looks like the derivative of cosine at x equals 2. So I kind of think that this thing is going to converge to negative sine of 2. This is kind of a tricky little like difference quotient thing that I threw in here, but I think that's going to converge, and I think it's going to converge to negative sine of 2. Of course, written another way, it could be cosine of 2 plus delta x minus cosine of 2 all divided by delta x, the limit as delta x heads towards 0, because delta x heading towards 0 is the same thing as 1 over n, where n approaches infinity. So it's kind of interesting. So that's just a little intuition. We didn't go super into detail about that, but we did think about it. Now we transition. What is a series? So a series is a sum of terms in a sequence. So if you have a sequence and you add up a bunch of those terms, you get a series. So interestingly enough, a series is just some number. At the end of the day, a series just gives you a number. Coming back over here to a sequence is a function. So a sequence has to be a whole list of things, whereas at the end of the day, a series is a number, or it's heading towards infinity or something, because we're just adding all these things up. It's a sum, so it's just some random number. No pun intended. What is a sequence of partial sums of a series? Okay, so this is a little bit confusing, I think. But let's say we had the sequence a sub n equals, let's just say n, just for the sake of it. Now that sequence, a sub 1 equals 1, a sub 2 equals 2, a sub 3 equals 3, a sub 4 equals 4, etc. If we wanted to make it into a series, we could start adding up those terms. Let's call it a sub n is equal to the sum of a sub n. So a sub n is our sequence. A series is just the sum of terms in a sequence. So a sub n, we'd sum them up. Now we might say that a sub 1 is simply the sum of the first term. So that would just be 1. A sub 2 would be the sum of the first two terms. That would be 1 plus 2, which is 3. A sub 3 would be the sum of the first three terms, 1 plus 2 plus 3, which is 6. A sub 4 would be 1 plus 2 plus 3 plus 4, which is 10. Now this right here is a sequence of partial sums. This is what we would call the first partial sum. This is what we would call the second partial sum. This is what we would call the third partial sum. And this is what we would call the fourth partial sum. Now you can see that's a sequence as well, because 1, 1, 2, 3, 3, 6, 4, 10, that's now a function. But the actual series, maybe it's a finite series of 4 terms, is just 10. The actual series, maybe it's a finite series of 2 terms, is just 3. Usually we talk about infinite series, so we're interested in adding up all of these terms. What does it mean for a series to converge? So in order for a series to converge, its sequence of partial sums must converge. So this is different because you're adding up terms. You're adding up 1 term, then 2 terms, then 3 terms, then 4 terms, and you're seeing if that converges to a number. Well, this clearly doesn't, because I'm heading towards something bigger. For instance, a sub 5 would be 15. So that is not going to converge, that sequence of partial sums. But it is different for a series to converge versus a sequence to converge. Sequence, you're just approaching infinity. For a series to converge, you want to add up from, say, n equals 1 to infinity, all of these terms, and see if you just get some number L. And to do that, you can look at the sequence of partial sums. So let's look at these series. They are, in parentheses, it says infinite series because they go towards infinity. And let's see if we think they converge or diverge. Well, 1 over 2 to the n from 1 to infinity. Now remember, we're adding all these things up. So do we think they converge or not? Well, it would be 1/2. Then we'd have to look at 1/2 plus 1/4. Then we'd have to look at 1/2 plus 1/4 plus 1/8. Then we'd have to look at 1/2 plus 1/4 plus 1/8 plus 1/16. I think that this number that we're adding on is getting pretty small. So I'm going to say I think it converges. This one, starting at 10 and going to infinity, has just taken off the first 10, terms here. So if this one converges, I think that one will too. This one, no way, because that's like 2, and then I'm looking at 2 plus 4, and then I'm looking at 2 plus 4 plus 8, and then I'm looking at 2 plus 4 plus 8 plus 16. These things are just getting bigger and bigger and bigger. No way is that going to converge. This one, well, if I plug in 5, I'm going to get 0. So that would be 0. If I plug in 6, I'm going to get 2. So that'd be 0 plus 2. If I plug in 7, I'm going to get 0. So 0 plus 2 plus 0. If I plug in 8, I'm going to get 0 plus 2 plus 0 plus 2. So this does not look like it's going to converge. I'm going to say diverge. This one right here, -1 to the n. I mean, plugging in 3, you get -1. Plugging in 4, you get 1. So that would be -1 plus 1. Plugging in 5, you get -1 again. So -1 plus 1 minus 1. This is -1, that's 0. This is -1, that's 0. And I think that that thing is going to diverge, bouncing around. This one, not sure, because it's going to be, my first term in the sequence is 1. Then if I add it to the next one, I get 1 plus 1/2. Then the next one I would get 1 plus 1/2 plus 1/3. Then I would get 1 plus 1/2 plus 1/3 plus 1/4. I don't know. It's getting smaller what I'm adding, but not as fast as this one. So I'm not sure about that one. Ooh, this one gets small pretty quickly though. 1 over 1, and then 1 over 1 plus 1/4, and then 1 plus 1/4 plus 1/9, and then 1 plus 1/4 plus 1/9 plus 1/16, and then 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25. These last things that I'm adding are getting real small, so I kind of think this is going to converge. This one, multiplying by 0.9 a ton of times. Every time you multiply by 0.9, it gets smaller. I'm going to say converge. And over here, I'm going to say converge as well. You can think about why that might be. So the really important thing to take away from this is that, hey, a sequence is just a function where your inputs are integers, and you just have these terms. A series is a sum of terms in a sequence. And to see whether they converge, sometimes we look at the sequence of partial sums, which is these partial sums here. So that should give you an idea about sequences and series.